Hello and welcome to Tech Simplified TV. Today we have a marathon episode based on variability and timing. Here we will try to understand how the changes in process, voltage and temperature affect chip performance, timing and yield. These PVT variations influence mobility, threshold voltage and delay. So accurate modeling is very essential. We will also touch on FEOL, MEOL and BEOL where transistor contacts and interconnects are formed to understand how variations start during fabrication. Then we will cover process corners like TT, SS, FF, which represents typical, slow and fast silicon, and also RC corners that model resistance and capacitance after layout. Using both PVT and RC corners help us sign off timing accurately. As chips shrink, variations become local even inside the same die, making timing analysis more critical than ever. So, if you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, challenges to build CMOS. Second, variability and level of abstraction. Next, process variation. Next, voltage and temperature variation. Next, design corners. After that, sources of process variations. There are 2 slides on this topic. After that, impact of process variations on carrier mobility. Impact of process variations on gate oxide capacitance and threshold voltage. Impact of process variations on W and L of MOSFET. Impact of variations on yield, delay and energy. Next, analysis methods for studying variability. And finally, modeling variability. So today we will cover all these topics to understand impact of variability on device performance and the reasons which contribute in variability. So we are done with this slide. We will move to the next slide. Challenges to build CMOS. In today's era, we fabricate millions of transistors. Fabrication of such huge number of devices flawlessly is a tough task. So it is challenging to fabricate millions or billions of transistors which will work flawlessly for 10 to the power 18 cycles. We have to fabricate in a way so that the transistors work reliably. They will perform as they are intended to work, and that it will do continuously for huge number of cycles. That's the biggest challenge. Now, transferring exact shape to silicon wafer or creating uniform doping profile are challenging. VLSI is basically a concept to reality process. First the concept, then the design. Design is transferred on the silicon. A transistor is basically transferred on silicon by layout, and layouts are geometrical structures. So suppose on pen and paper or on software, this shape has to be transferred on silicon, although when it's transferred on silicon, it doesn't remain same. Transferring exact shape to silicon wafer, that's a challenge. Another challenge is maintaining uniform doping profile. When we see the cross section of a MOSFET, we see that this part is source, this is drain. So these are the highly doped zone and this is very lightly doped zone. So this doping profile, although in this zone it's not very uniform. In this zone it's not very uniform. This uniform doping profile creation is a challenge. These are basically practical challenge when we are fabricating or developing the chip by individual steps. Now operating condition might range from freezing to boiling. So first 2 are manufacturing related challenge we have mentioned. Now it's operation related challenge. Functional chip, now it's in operation and the condition in which that chip is getting operated, that is not fixed. temperature might range from freezing to boiling. Intense electric fields gradually break down the gates. A chip is getting used for longer times. Continuously electric current is flowing on gate. Continuous voltage is applied. Intense electric field can gradually break down the gates. Continuous flow of current carry away atoms of wires. That is electromigration. Now, another issue is cosmic rays zap the bits stored in a tiny memory cell. Memory cells are there and each of them have some bit stored in that. So a stored bit can be changed because of interference of cosmic rays. That could be a challenge. Another is manufacturing or environmental variation has impact on chip. This temperature is going up, down. Continuous electrical field is carrying away the atoms of the wire. So basically structure of wire or interconnects getting changed. So all of these manufacturing variations, environmental variations, this all has impact on chip. They have impact on individual MOSFETs, and overall these impacts sum up and manifest or come out in front of us as impact on performance. Now design must include impact of manufacturing variations and changing operating conditions. So there are three different sources of variation. First is process variation, P, supply voltage variation, and operating temperature. So P, V and T. We all know that because these P, V, T or P, T, V corners are mentioned. These are basically this variation of process, supply voltage and operating temperature originates from there. Our aim is to design a circuit that operates reliably over all extreme P, V and T. Otherwise, this can cause poor yield and circuit performance. If we do not consider variation or impact of this variation of P, V and T, that could lead us to poor yield and circuit performance. So these are basically challenges to build CMOS. We are done with this slide. Now let's move to the next slide. Variability and level of abstraction. So here is a diagram. We have used this diagram to understand what is happening. This is the basic process. The process we use to fabricate chip, such as oxidation, requires heat, ion implantation. And in case of ion implantation, ions are implanted on the wafer with high energy and dose. Lithography is transferring a shape on the wafer. Now chemical mechanical planarization, these all are the source of process related variability. Now temperature might vary, dose that might also vary, and energy, a slightly difference can impact the process. Wafers are processed in batch. In one batch, fixed multiple numbers of wafers are processed. These are called lot. We will see in some later slide. In second lot, while doing this ion implantation, suppose the dose or energy is slightly different from the previous lot. And if we suppose that in one lot, n numbers of wafers are processed, so first batch of n wafers are processed, especially ion implantation for those n number of wafers has been done with some dose and energy specification, and for next batch of n wafers, this ion implantation has been done with dose or energy slightly different from the previous run. So this ion implantation, how much these ions penetrate and where it would have the highest concentration, how many numbers of ions will be implanted, that might get changed because of this change, because these ions are activated with energy. That's why they move and penetrate and go into the wafer. So if that energy is changed, the profile might get changed. And accordingly, when wafers from these two lot perform, their performance might vary. Due to process, here variability get introduced in the device. Now, random variation in operating conditions such as temperature and the power supply voltage VDD increases with circuit clock frequency, leading to circuit performance variations. We are talking about when the circuit is in operation. This degrades yield and increase production cost. So from one to another, this gets changed. Now, variation of performance metric of a circuit like delay, dynamic power and static power consumptions ultimately propagate their negative influence on overall performance of a chip. So, this temperature, dose and energy, they make process step in one run to different from the second run. Process variation parameters contribute mostly in case of device structure and doping profile. That means the basic parameters or basic behavior of the device is slightly different from the other, along with the environmental factors that basically decides the device characteristic. And this device characteristic along with this temperature, VDD, that is environmental factors, that decide the circuit characteristic, and overall circuit characteristic with environmental factors controlling the chip behavior or deciding the chip behavior. And overall, if this device characteristics or circuit characteristic is hugely deviated from what we have expected, that actually impacting the yield, and if yield is bad, so cost is high. So we are done with this slide. We will move to the next slide. Now process variation. Here we can see lot to lot variation, wafer to wafer variation, chip to chip or across wafer variation, and on chip variation. So we will now understand what are these things. So process variations can be classified as lot to lot, that is L to L, wafer to wafer, W to W, die to die, that is D to D, inter die, or within wafer, that is WIW, and within die, WID or intra die. Now let's understand in a little bit detail. Lot is batches of wafer. Usually wafers are fabricated in batches. So in one batch, n numbers wafers are processed. That is one lot. Once it's done, then another lot is done. Each one has n number of wafers. And we always try to maintain same physical condition, same temperature, same energy, everything. Still, so this die is different from this die or from this die because of process variation. This difference or variability between two lot, we call it lot to lot. Now wafer to wafer. Let's concentrate on one lot. Even in one lot, two wafers, these dies, they have variability. So this is called wafer to wafer variability. Now die to die. Now let's concentrate on single wafer. From this wafer to this wafer, the same position, same die is different from this to this to. Now die to die. In a single wafer, so many dies are there. So this die is different from another die. That is die to die or inter die or within wafer. Inter die between two dies on same wafer or within wafer. This one. Third. And fourth one is within a die, there are huge number of MOSFETs. One MOSFET is different from other. That is on chip or intra die or within die. These are four types of variation. So variability in lot to lot, wafer to wafer, and chip to chip are almost equally applied to every transistor on chip. These inter die variations are called global variations, and remaining within chip or intra die variations referred as local variations. And these three are global. That is lot to lot, wafer to wafer, and chip to chip. These are global variations and this is local variation. Now global and local variations must be modeled accurately. That helps in estimating the power and performance scaling of the circuit complexity. During analysis, we must model this variability. Otherwise, we can never estimate the yield or performance. That estimation will be wrong. So local variations get averaged out for large number of transistors or long critical paths. And global variations usually add up and shift the average power performance of the entire chip. Now D to D or die to die variations make one chip faster, slower than another. And within die or intra die variation become important in nanometer processes. So this one is very local thing is very important for nanometer processes, and die to die variations mean one chip faster or slower. So we are done with this slide. We will move to the next slide. Now voltage and temperature variation. Systems are designed to operate at nominal supply voltage, but this voltage may vary for many reasons, including tolerance of voltage regulator, IR drops along supply rails, and DIDT noise. Typically, the supply is specified at plus minus 10% around nominal at each logic gate. In case of supply voltage, it's defined like 5 volt plus minus 10%. We define it in that way. The supply varies across the chip as well as in time. Speed is proportional to operating voltage VDD, and this leads to plus minus 10% delay variation. speed is proportional to VDD, and this supply voltage which is coming as a VDD that has 10% variation, speed is also 10% variation. So opposite of speed means delay. If speed is high, that means delay is less. If speed is less, so delay is high. So delay, in other terms, delay is also getting varied by 10% plus minus. As temperature increases, drain current decreases. The junction temperature of a transistor is the sum of ambient temperature and the temperature rise caused by power dissipation in the package. This rise is determined by power consumption and package thermal resistance. Junction temperature of a transistor is the sum of ambient temperature and temperature rise caused by power dissipation in the package. Packaging. It's not only fabricated, it need to be packaged properly. Junction temperature transistor is sum of this ambient temperature and temperature rise caused by power dissipation in the package. And this rise, how much this temperature of that chip will rise, determined by the power consumption of the total circuit and the package thermal resistance. So ambient temperature ranges for parts specified to commercial, industrial and military standards. So use for which purpose the chip is getting used according to that this specification that are mentioned. Like here is a chart. So standards are commercial, industrial and military. Commercial is minimum 0 degree, maximum 70 degree. Many industrial processes temperature is higher temperature than normal operation. So usually commercial is minimum 0 degree and maximum 70 degree mentioned. Industrial minus 40 degree, 85 degree. In both cases, the range in industrial is wider compared to commercial, and in military is the harshest condition. The highest range is provided for military application. Now temperature varies across a die depending on which part dissipate the most power. The variation is gradual, so all circuits in given 1 millimeter diameter see nearly same temperature. Temperature across a die also varies depending on which part dissipate the most power. The variation is gradual, obviously. So the circuit in a given 1 millimeter diameter see nearly same temperature. This is about voltage and temperature variation. We are done with this slide. We will move to the next slide. Design corners. The collective effects of process and environmental variation can lumped into their effect on transistor. Typical, that is also called nominal, fast or slow. T, F and S. When these processing variations are combined with environmental variations, we define design or process corners. The term corner refers to an imaginary box, this one, that surrounds the guaranteed performance of circuits. The corners are specified with 5 letters describing the NMOS, PMOS, interconnect, power supply and temperature respectively. The letters are F, T and S for fast, typical and slow. Fast, F, typical T and slow S. So basic nomenclature, NMOS can be slow, typical and fast, that is S, T, F. PMOS can be slow, typical, fast, that is S, T and F. Next, temperature can be hot, typical, cold. If temperature is hot, device will be slower, so it is S, typical and cold, so fast. VDD can be high, typical, low. If VDD is high, that is fast, typical T, and low, that is slow. Example of process corners and their detailed descriptions. So example of process corners and their detailed description. Process corner label may include NMOS, PMOS, temperature and VDD. So T means typical NMOS. First one is NMOS, then typical PMOS, then T means room temperature, that is typical or nominal, and then T, nominal supply, and this SSSS means slow NMOS, slow PMOS, temperature slow if it's hot, so hot temperature, and low supply. Supply is low, that is S, so low supply. FSSS, that means fast NMOS, slow PMOS, slow temperature means hot temperature, and slow supply means low supply. So we are done with this slide. Let's move to the next slide. Now sources of process variations. In first two slide we have mentioned these steps include variability. Now let's see how it happens. Lithographic variation. Uniformity of a printed feature size depend heavily on control of the lithographic imaging system. A small vibration in the apparatus can lead to non-uniformity of the critical dimension of printed lines and significantly change the speed and leakage of CMOS transistors. In FinFET episode also we have mentioned that lithographic variation means typical wavelength is coming out from the machine and it's transferring a shape on the wafer. Small vibration in the apparatus can create a non-uniformity. Now line edge roughness, it is deviation in feature dimension from intended shape arises from variation in lithography and etching process. If this one is the intended shape, perfect rectangle, when it's transferred it's like this, deviation is there. We take it as a mean position, then this way, that way, this way, that way, it's moving. Now random dopant fluctuation. Random dopant fluctuation refers to the random microscopic fluctuation of the number and location of dopant atom in the MOSFET channel region. It causes fluctuation of transistor electric parameters such as threshold voltage, short channel effect and drain induced barrier lowering. Dopants are here, although they are fluctuated, their positions, density is not same across all position. Here the density, here the density, all are different. This is not same, not uniformly distributed. That is dopant fluctuation. Numbers and location of dopants in the channel region, not uniform. So RDF, that is random dopant fluctuation, is also another cause of variability. Now let's move to the next slide. Sources of process variations. Well proximity effect and STI and length diffusion. Advanced CMOS technology use high energy implants to form deep retrograde well. During implant process, atoms can scatter laterally from the edge of the photoresist mask and become embedded in the silicon surface close to the well edge. This is the resist so that the implant doesn't come here. We need to protect this area. We are forming this well. They are getting scattered and their direction is diverted. Vertically also coming and scattered also coming. So here effective density became higher. We have tried to show it with shading, color shading. As a result, well surface concentration changes with lateral distance from mask edge. This is the edge of the mask. From here, this density changes because here both from vertical direction implant is coming and the scattered implant is also coming. So in this zone the concentration is higher. Over range of 1 micrometer or more. As a result, well surface concentration changes with lateral distance from the mask edge over range of 1 micrometer or more. Threshold voltages and other electrical characteristics also vary with the distance of the transistor to the well edge. This phenomenon is known as well proximity effect. Here, implant concentration, surface concentration is changed and accordingly the parameters like threshold voltage, other electrical characteristics, that also vary with the distance of the transistor to the well edge. Now STI and length of diffusion. Shallow trench isolation and length of diffusion. STI is forming trench and filling it with non-conducting material to isolate active regions. So this is one device, this is another device. Here shallow trench isolation is done to isolate from this to that. These filling materials exert compressive stress to vicinities. Compress this area. Tensile stress or compressive stress can change the mobility in silicon. So that is basically mechanical strain. Mechanical stress is there. So this filling material exert compressive stress to the vicinity, that is in diffusion areas. In diffusion areas they give stress. This stress is commonly referred as STI stress, also called length of diffusion effect, where the characteristic of a device vary according to the distance of its gate from the diffusion edge. Mechanical stress change free carrier mobility. That is the basic principle of strain silicon. Using mechanical stress, actually silicon is strained and mobility changes. We have came across this thing in strain silicon episode. So consequently, transistor with same gate size but a different LOD have very different speeds. The stress increases as the channel to STI active edge distances decreases. Channel to STI distance, depending on that distance, the amount of stress is changed, and amount of stress is changed means impact on free carrier mobility is changed. So one transistor always behave different from the other. So that is STI and length of diffusion effect. So we are done with this slide. We will move to the next slide. Impact of process variations on carrier mobility. So the MOSFET parameters are affected by relevant process step. A single process step can affect multiple transistor parameters. Decoupling the effects of one variation source from another is extremely difficult. Look at this chart, we can easily understand that. Mu, that is mobility, is impacted by ion implantation, diffusion, annealing and stress. Gate oxide capacitance is impacted by gate oxide formation. WNL, that is width and length, that is impacted by etching and lithography. And VTH is impacted by ion implantation, gate oxidation, annealing, etching, lithography. So lithography is mentioned here and here also. If we consider length and width, etching and lithography both has contribution in that. In case of change of mobility, ion implantation, diffusion, annealing, stress, multiple steps contribute in that. So segregating or decoupling which one is affecting is really difficult. Now let's see how carrier mobility is impacted by process variation. Mobility is the ability of carriers, or that is both electron and holes, to travel through the channel of a MOSFET with an applied electric field. Mobility of carriers in channel is impacted by doping concentration since it determines the mean free time between collision. So mobility is ability to travel through channel under electric field. Now if doping is higher, number of dopant is higher, that is channel area is more crowded, mean free path decreases. Mobility of carriers is impacted by doping concentration since it determines the mean free time between collisions. The dose and energy of ion implantation and annealing temperature directly influence mobility since these process steps primarily determine doping concentration. Dose and energy of ion implantation and annealing temperature directly influence mobility. Now strain engineering of a device channel either by using local techniques such as nitride liner and silicon germanium in source drain or global techniques such as silicon germanium substrate affect the device mobility. We know strain can change. Unintentional stresses induced due to STI can cause intra-die mobility variations of few % depending on transistor distance to the STI edge. Just in last slide we have discussed that. Introduction of strain can change. That is also a variability one device to another, from one circuit to another. Dose, energy and ion implantation, all these impact the carrier mobility. Doping also impact carrier mobility. Now introduction of STI, which is very important step, important for isolation, that creates unintentional stress. All these parameters, they affect the carrier mobility. So we are done with this slide. We will move to the next slide. Now gate oxide capacitance, COX and threshold voltage. Gate oxide thicknesses are scaled to atomic level on order of 5 atomic layers, that is 10 angstrom. A small change in one atomic layer can greatly impact on not only oxide capacitance but also the threshold voltage and mobility of MOSFET device. A small variation in thickness of just one atomic layer would result in 20% variation in gate oxide thickness. Controlling this variation is difficult due to physical limitation at this atomic scale. In state of art or nanometric devices, this impact of variation is impactful because already device dimension is reduced. This gate oxide thickness has scaled to 5 atomic layers, that is 10 angstrom. A small variation in thickness of one atomic layer results in 20% variation. So that's huge impact. Now use of high K dielectric material as good gate oxide results in moving to a new gate oxide material not only reduces gate leakage current but also reduces the impact of variability on COX due to much larger physical oxide thickness. However, variation in oxide of high K stacks interfaces are still problematic and can also affect performance. Now high K stacks are also there. Handling high K stacks is also problematic. So now threshold voltage. Threshold voltage determined by number and location of dopant atoms implanted in the channel or halo region. Ion implantation is a stochastic process leading to random dopant fluctuation that causes VTH to vary. Impact of statistical distribution becoming even more significant as device dimension reduces. The variations have become large in nanometer process because the number of dopant atom is small. When the dimension is small, a small change in number of dopants can give a huge impact. So this variability actually impact gate oxide and threshold voltage. We are done with this slide. We will move to the next slide. The impact of process variations on W and L. Transistor dimensions. So the saturation current shows that the width and length of transistor influence the device current. processing steps and related factors like the wafer mask, exposure time, etching process, spacer definition, source drain implantation, and even the environment during the manufacturing process contribute to the overall variation in gate length and width. Any variation in channel length is directly reflected in device delay, which is directly proportional to the channel length. Here ID is proportional to W and inversely proportional to L. So shrinking of device channel length is physically limited by patterning wavelength, where lambda is 193 nanometer for 45 nanometer technology node. Therefore, patterning a very short channel length below this wavelength become extremely difficult to control, leading to an increase in gate length variation. If we scale down the device dimension, accordingly we have to scale down other things. The patterning wavelength, which is used for 45 nanometer technology node, that is 195 nanometer wavelength. Patterning a very short channel with this wavelength is difficult and variation get introduced there. On and off current. From this current we can easily understand that W and L is always related to the current. So both on and off current has dependency on L and W. So small change in process variation causing variability in L and W finally result in transistor performance variation. If transistor dimension changes, since I on and I off, on and off current has a dependency on this dimension L and W, definitely that will get changed. So I on and I off also impacted with process variability. We are done with this slide. Let's move to the next slide. The impact of variations on yield, delay and energy. In CMOS, yield indicates the fraction of products that are operational. It is probability that a particular product will work. So failure probability is expressed as x equal to 1 minus y. Design techniques and analysis tools are used to minimize range of variability. Variability more than permissible range cause failure and thus yield reduces. At each node, dimensions get smaller and thus a constant variability actually means greater percentage of change. Small percentage of variability create larger impact in this dimension. Variability more than a permissible range considered as failure. At each node, dimension is reducing and variability remains same, then that is a huge impact. That's a huge percentage. So small percentage of variability at one node can create huge impact next advanced or smaller node. Now delay. A change in on current changes the delay of an inverter by the same fraction. An M input gate will have up to M transistors that can vary separately. Suppose a circuit is there where M numbers of inputs are there. It's an M input gate and M transistor that can vary separately. The delay of N stage path is sum of delays, and this in this system there are suppose number of stages are there. Number of input is M and number of stages are N. Suppose here like these stages are there. The delay of N stage path is sum of delays through each stage getting added. Delay gets added. Now if the variation are completely correlated, the delay of path will have same variance as the delay of gate. However, if the variations are independent, the variance introduced by factor N cross M. Number of input is higher, all of them are varying separately and stage is N and delay is getting added. So altogether this variance becoming a huge. So delay of N stage path is sum of the delays through each stage. If the variations are completely correlated, the delay of path will have same variance as the delay of gate. However, if the variations are independent, the variance reduces by a factor of N cross M. Now energy. Variation has a minor impact on dynamic energy. It has major impact on static leakage energy. Static leakage energy is exponentially sensitive to threshold voltage. Systematic variation in VT makes a tremendous impact because all transistors are correlated and exponential as a long tail. Variation has impact on yield, delay and energy. We are done with this slide. We will move to the next slide. So what are the analysis method of studying variability? Variability is there, we know, and we must analyze them properly to include in our modeling so that their impact is included. Digital circuits are designed in a way so that circuit should meet the performance specifications such as speed, power consumption and under all operating conditions. Statistical fluctuation in semiconductor fabrication processes leads to undesirable circuit performance. It's necessary to model manufacturing process variations to predict the device and circuit performance to minimize the impact of parameter variation on circuit performance and maximize the yield. There are different general techniques and methodologies used to handle the impact of process variation. One is worst case corner analysis, Monte Carlo analysis, design of experiments and response surface modeling, and sensitivity analysis. These are standard methods used to analyze the variability. It's really important. If we do not understand it and model it and try to minimize it, we can never maximize the yield. We always try to minimize the variability and maximize the yield. All these 4 techniques are mentioned here: worst case scenario, Monte Carlo analysis, design of experiments and response surface modeling, that is DOE RSM, and sensitivity analysis. These are the methods, analysis methods. We are done. Move to the next slide. Modeling variability. So let's talk a little bit about how variations are modeled with uniform distribution or Gaussian distribution. So uniform distribution refer to a type of probability distribution in which all outcomes are equally taken. Uniform distribution are specified with half range A. Here we have taken an example, VDD as 1 volt plus minus 10%. We are defining it as uniform distribution 1 volt and plus minus 10% here. Here half range is 100 millivolt. Normal distribution, also known as Gaussian distribution, a probability distribution that is symmetric about the mean. This is the Gaussian distribution, and this is specified with a standard deviation X. Processing variations are usually modeled with normal distribution, and circuit designer commonly treat process variations as combination of global variation and local variation. This method lumps up all the chip to chip and wafer to wafer variations into one global variation component, and the remaining variations are one local variation component, like this. We have mentioned there are global variation and local variation. So global variation, so all variations are together, global and local variations. These are inter-chip and intra-chip. We consider all across chip, random variation, everything is included there. So circuit designer actually lumped all these chip to chip and wafer to wafer variation into one global variation component, and the remaining variation as one local variation component. And this way variation is modeled. So we try to give you an idea how process related variability, intentional, unintentionally introduced variability impact the end product, that is the chip performance. So we are done with this slide and we are done with today's episode.
Hey guys, welcome back to the computer screen. In today's episode, we are going to cover the below topics. We will do a quick recap of the semiconductor fabrication process or CMOS. Next, we will do the categorization by end of line for the entire CMOS process. We will explain different end of line parts by a vertical cross section of a chip. We will go further in detail in front end of line. Then we will cover the middle end of line. Then we will cover the back end of line. We will show the different end of line sections inside a CMOS layout. Then we will point out the FEOL and BEOL parts which are designed through the physical design steps. Once all these points are discussed, we will summarize the entire discussion. We are done with this slide, so let's move on. Semiconductor CMOS process. Here is the infographics by which we will recap already known fabrication process. It's in a cyclic manner, so let me start from one point. We do the deposition, then we do the photoresistive coating, then we use a mask and expose this photoresist to the mask layout, and accordingly imprint happened on the photoresist coating. Then we develop it and then we etch it, and then we do the needful ion implantation. Finally, we will be stripping out the remaining photoresist, and this kind of process keeps on repeating for different zones and different dopants in the entire semiconductor wafer. And this particular mask is designed in physical design, which is taped out as GDS2. We are done with this particular slide, so let's move on. Now we will categorize the entire CMOS fabrication into 3 different sections as per the actual semiconductor fab process divisions. The first part is called the FEOL or front end of line. The next part is called the middle end of line. And the last part is called the back end of line, that is BEOL. In front end of line, we develop the transistor level layout design into the silicon wafer. In middle end of line, we do the transistor level interconnect. Keep it in mind, this level of interconnect is only for the transistor level. And in back end of line, we do the PNR level interconnect. So once your GDS2 is ready, during the actual semiconductor fabrication process, it fits into three parts: FEOL, MEOL and BEOL, according to which the different stages are fabricated or developed. We are done with this particular slide, so let's move on. Vertical cross section of chip. So here in this picture you can see the vertical cross section of a chip, and this is taken from Wikipedia, so you can go ahead and also look it there. You can see it clearly. So let me point out where the different end of line processes resides. So here resides the FEOL part. So it's the fabrication of the transistor and other active or passive devices on silicon. Next, the transistor level or the active or passive level device interconnections are done through the MEOL process. So this is a very low level connection. You can see we have not used any vias or higher metal layers. So it's very minimalistic interconnect. And the rest of the interconnect, whatever we do in the PNR level, in the SoC design, or specifically in the physical design process of the SoC design, all those interconnects, that is the metal and via layers, are fabricated through the BEOL process. So this explains what are the things. So front end of line, then mid end of the line, and then back end. So this explains the three process: FEOL, MEOL and BEOL. We are done with this particular slide, so let's move on. Front end of line. This whole geometric representation come out of physical design is called integrated circuit layout. The wiring is termed as routing. The physical design makes room for the FEOL, MEOL and BEOL during fabrication. The front end of line is the first portion of the IC fabrication, where transistor, capacitor, resistor, etc. are fabricated as per the layout made in the physical design. FEOL consists of the chemical mechanical polishing, also known as, and cleaning of the wafer. Shallow trench isolation, STI or LOCOS, it is applicable for technology node greater than 0.25 micrometer, comes under the FEOL. FEOL also include well formation, gate module formation, source and drain module formation. So this gives a clear snapshot of the FEOL. We are done with this particular slide, so let's move on. Middle end of line, MEOL. MEOL consists of semiconductor wafer process steps that create local electrical connection among source, drain, gate of transistors. Most important part of the MEOL is the gate contact formation. It occurs after front end of line, that is the transistor, design capacitor, design resistor formation are complete. Before the back end of line, metal via or isolation dielectric formation process. It's in the middle. You can understand by its name. We are done with this particular slide. Let's move on. Back end of line, BEOL. The back end of line is remaining portion of the IC fabrication, where the wiring is done through the metallization or vias, including dielectric separators among various metal layers. And it goes like silicidation of the polysilicon and source drain diffusion, then adding a pre-metal dielectric and CMP, polishing it, then making holes in PMD and create contact through it, adding metal layer 1, then also known as the intermetal dielectric, adding it to CVD, make vias through the IMD to connect lower metal layer with the higher metal layer. Carry on the last step until all the metal layer are as per the particular tech node are done, and add final passivation layer to protect the entire chip. We are done with this particular slide, so let's move on. So here we will show you a CMOS layout, and during that process I will point out that where the FEOL is, where the MEOL is and where the BEOL is. So let's start. In left side will be the NMOS part and right side will be the PMOS. This is N-well on which our PMOS will be created, and this is the P-select layer, and this is the diffusion layer, and here you can see the N-select layer and the diffusion layer, and here goes the source, drain, contacts. So before creating the contacts, all these things which were fabricated were in the FEOL. As soon as we put the contacts, our middle end of line MEOL starts. and then we have the poly gate connecting them. So here also this gate connection formation comes under the MEOL. This is our poly gate, and then we connect source drains as per the CMOS. Here it goes to VDD, and here it goes to ground. And this layer, whichever is now I have just shown for interconnection, this is metal 1, and this kind of source drain connection among the transistor, this is at the MEOL. And here the contact is created for the output, and anything beyond, because now I cannot grow the thing vertically because that will grow towards you. Anything beyond this goes for the back end of line. So this is a typical example. In case of different devices, you can now understand what to be in the FEOL category or whatever in the BEOL category, and what comes in between, that is MEOL category. So this is kind of these divisions are part of the semiconductor fabrication process, and these terms are highly related to the foundry where your chip is made. We are done with this particular slide, so let's move on. FEOL and BEOL in the physical design, and I'll also point out the MEOL here. At left side will be our analog layout design, that is the layout by hand, and right hand side will be the physical design part of the SoC design. In the left side you can also say the IP design part, where we define the IP layout by hand, say by some tool like Virtuoso, and right hand side we will use a tool like ICC or Encounter. So this is the two different parts where the FEOL part is handcrafted by you and the BEOL part is handcrafted you, and somewhere in the fine part lies the middle end of line. I will also point it out. So here goes the schematic design, and the flow will go in the direction of the arrow. Then is the layout. Next is the DRC LVS. Then goes the RC extraction. Then comes the physical verification. And finally the characterization and delivery. So this is a very short and sweet part, that is the backend part of the IP design, or you can say the analog design, whatever applicable to you where you are working. And this stage already, this is we have talked about the backend part of the analog or IP design. Now we go towards the physical design part of the SoC design. So first, once the front end design is done, then we go for the floor planning and PNR. Then we have the DRC and LVS. Then we go for the RC extraction. Then we go for the ST and all the types of physical verification, including EM, IR checks, all those things, antenna checks and all those stuffs. And finally, we do the formal verification and sign off. So this is in a nutshell the backend part of the SoC design. That is on the right side, and left side is for the IPs or the analog design. This part covered by the purple box is where the FEOL is designed by a layout engineer by hand, and once the FEOL is done, also MEOL is also done here. So this is the typically you do the design, and which actually getting utilized in FEOL resides here, because in the physical design part of the SoC design mostly the standard cells are used, so they are only placed and interconnected. You don't do the actual go into the each individual cell and edit their layouts. What you do in the your analog or IP design at the left hand side. So here the purple box covers where the BEOL part is taken care. That means I am talking about not only the design also, but for the verification. That means you scrutinize them and check them, all these things. That's why I kept multiple steps inside the box. You can see the FEOL and the MEOL goes in the left hand side, and where the BEOL part goes in the right hand side. So I think I have given you a bird's eye view how this FEOL and BEOL resides in where, in which area of the VLSI design. So we are done with this particular slide. So let's move on. Summary. FEOL generally covers everything up to but not including the deposition of metal or via interconnect layers. MEOL consists of semiconductor wafer processing steps that create local electrical connection among source, drain, gate and off transistors. BEOL is the remaining portion of the IC fabrication where the individual active or passive devices get interconnected with wiring. For modern IC process, more than 10 metal layers can be added through BEOL. All the three EOL are taken care to physical design in VLSI. When I say physical design, I mean the physical design part of both the IP design and the SoC design. So both are huge covers the EOL. So we are done with this particular slide. So let's move on. Hey guys, welcome back to the computer screen. In today's episode, we are going to discuss the below topics. We will cover the basic CMOS layout and point out the basic PMOS versus NMOS fundamental difference. Then we will do a quick recap of the semiconductor CMOS process. Next, we will do a short and sweet introduction to the CMOS process variation. Then we will become familiar with the process corners, also known as the FEOL corners. Next to it, we will show you a common graphical representation of the process corners. Next, we will talk about the FEOL and BEOL corner terminologies that are most frequently used in VLSI. Next, we will deep dive into the detailed nomenclature of the FEOL corners. Next, we will talk about the process corner variation. Finally, at the end, we will summarize the entire discussion. So we are done with this particular slide. Let's move on. CMOS layout, a quick tour. Here, this slide is to build the connectivity of the entire theory that we are going to discuss today. So we are starting from the very basic level of the CMOS layout. Now, it contains a NMOS and a PMOS. Here goes our N well, and inside it we have a P select. Then we have the diffusion layer. For the NMOS, we have the N select, and inside it we have the diffusion layer. For the PMOS, we create the source and drain contacts. Similarly, for the N select, we introduce the source and drain contacts for the NMOS. Then we create the poly gate to connect them. Next, we will connect source and drain of the PMOS and NMOS. This goes to VDD and this goes to ground. And from here, we will take the output. Input will be in the poly. So this is the basic CMOS layout. And the reason why I have shown you that here the process corners mostly depend upon two terms, one belonging to NMOS and another belonging to the PMOS. However, at the very basic level, when you are asked in interview, you may ask this question: what is the basic difference of NMOS versus PMOS? I'll come to the details. Here, let us go through the graphical representation. Now, generally, we make the area of the PMOS twice the NMOS area. We'll come to the reasons in the next slide. We are done with this particular slide, so let's move on. PMOS versus NMOS, the fundamental difference. Mobility of electron is twice as compared to the hole in PMOS. On resistance of the NMOS is half of PMOS. Consequently, to balance out the same channel resistance and mobility, PMOS is made twice larger in size with respect to the NMOS. A CMOS contains this balanced NMOS and PMOS pair. Stopping here, I'll tell one thing, that for the process corner, we will be mostly focusing on the speed. So the corner variation or the process variation here will be focusing on the speed of the NMOS and PMOS. Before doing the variation, we are doing the balancing at the very bottom here. If we do not do the balancing for the same dimension of PMOS is slower than the NMOS by birth. We are mitigating this by making the double size of the PMOS with respect to the NMOS. However, PMOS circuits have following advantages over NMOS. This is a few good things for you to know. CMOS technology is highly controllable. It is low cost process. It has good yield and high noise immunity. If not, CMOS, NMOS based ICs can be smaller for the same complexity and silicon area as compared to its CMOS counterpart. So folks, with the layout and this particular slide, that means the previous slide and this slide, we have made the basic ground clearance of the PMOS versus NMOS difference, and we have balanced out the path defect of NMOS versus PMOS with respect to the speed. We are done with this particular slide, so let's move on to the next slide. Semiconductor CMOS process, we will be doing a quick recap. You already know about the CMOS process. We are going through a quick recap so that once we talk about the process variation, this image will be there in front of your mind. This process happens in a cyclic manner for multiple steps. So we'll start with the deposition. Then we do the photoresistive coating. Then we expose the mask with the UV light. Then we do the developing, then we do the etching, and then we do the ion implantation. And at this stage, the threshold voltage or the speed is impacted. So this is a very important process step for you to remember. Next, we do the stripping of the photoresist, and the thing goes on and on in a cyclic manner for further layers. As I have shown you in the CMOS layout, right, different parts are created separately. All these parts which appeared separately in the animated format, which you have already shown, that will be done through the process steps moving in a cyclic manner. We are done with this particular slide, so let's move on. CMOS process variation. Parameters of a semiconductor fabrication are generally statistically distributed. That is mean, standard deviation, etc. You might be familiar with all these statistical terms. The variable process parameter list includes, we refer it with the capital P, threshold voltage of NMOS or PMOS. As I have mentioned already that an implantation has an impact here. Gate oxide thickness, TOX, poly line width, metal width, insulation oxide thickness. All these process parameter will have impact and goes under the process, that is the bold letter P. Variable operating condition include operating voltage or die voltage, that is V. Here V is a bold V, and the operating temperature, that is a bold T, within the range of -40 to 125 degrees Celsius. So these are the P, V and T. These three things are varied. Here we will be focusing on all of them and you will see the variations. The crucial factor here is to understand is the process, because the temperature and voltage, these are values. They can be varied very easily. For process, you have to know the details, which already I have displayed in this slide, and you can connect back to the previous slides with the layout and the semiconductor process and all the stuffs that I have already spoken. So done with this particular slide, let's move on. Process corners, which also known as FEOL corners. The term corner refers to an imaginary core box that ensures specific performance of the circuits at each of its corners. Each corners, that is the extreme limits, specify some sort of performance boundary condition for the design under consideration. We'll show in the graphics in upcoming slides. Process corners represent the extremes of silicon fabrication process parameter variation for a fabricated circuit. Mixed name corners like fast slow or slow fast are referred as Q corners. When the parameters of a transistor are set in such a way that the transistor operates fast, then it is known as the fast corner. A single circuit will perform differently in each of the process corners. A single process corner may slow slightly different performance for a given circuit from one wafer lot to the another wafer lot. Now, this is absolute process variation, because when we standardize a process, however, once we move from one wafer batch to the another wafer batch, there might become variation in the semiconductor fabrication process. The testing of the circuit performance at each corner is termed as characterization. This word is used frequently with standard cells. So you might hear about that standard cell characterization. So characterization is related to this particular point. Two-letter designation, that is TTFFSS, etc. point to N-channel MOSFET corner and P-channel MOSFET corner for a CMOS structure respectively. Two-letter designation TTFFSS points to N-channel MOSFET, NMOS corner, and P-channel MOSFET, that is PMOS corner, for a CMOS structure respectively. We are done with this particular slide, so let's move on. Process corner, the graphical representation. In last slide, we have talked about geometrical representation where all the corners we will find. Now, here in this slide, I'll show you. Here in x-axis, we have the NMOS speed, and in y-axis, we have the PMOS speed. All the slow NMOS are lying on this vertical line where x is constant and y is varying. And all the fast NMOS are lying in this line where x is constant and y is varying. Similarly, the slow PMOS line where y is constant and x is varying is this one, and the fast PMOS are lying in this line where the y is constant and x is varying. This is a Cartesian geometry where we have all the lines and the boundaries we have drawn. Now, in actual, when we have corners are of a parallelogram. So here is our parallelogram. This corner is slow. So you can see both slows are cutting there, and here it is fast. So you can see near to it, both the fast lines are cutting together. And this is slow, fast. So first is NMOS and the second is PMOS. You can see the lines are there. It's very near to this fast of PMOS, slow of NMOS. So it is SF. And here it is FS, where we have the fast NMOS and slow PMOS. You can see the lines are also close. So this is a very easy graphical representation. And of this parallelogram, where the diagonals cut each other or intersect each other, we have the typical corner, that is TT, lying there. So I have not drawn the diagonals. However, in imagination, you can draw them and you can see at the cut point of the two diagonals lies the TT. This is the corner representation, and you can well understand the extremities from this particular graphics. This SF and the FS are called skewed corners. You can understand why. So that's all with this particular slide. Let us move on to the next slide. Corner terminologies in VLSI. So we have two terminologies. First one is FEOL corners and the other one is BEOL corners. Now already in the last episode I have talked about the FEOL and BEOL processes. In case you have not watched, please go ahead and watch it from the playlist. The FEOL corners is FF, SS, TT, FS and SF. We have already shown this in the previous slide and in the graphics. BEOL corners are C worst, P best, PC worst, RC best, RC worst. These I have already discussed in the RC corners episode. In case you have not watched, please go ahead and watch that episode. So these are two type of terminologies in VLSI. First set is called the FEOL corners. In today's episode, we are discussing about this. And another episode, we have discussed about the BEOL corners, which are called RC corners. So FEOL corners are process corners and BEOL corners are the RC corners. We are done with this particular slide, so let's move on. Common FEOL corner names. So here we'll go through the common FEOL corner nomenclature. Here we are drawing a table. Here we'll go the name in the leftmost column, and in the first column there will be the NMOS and PMOS. So first is FF. So here NMOS is first and PMOS is first. So first F comes from NMOS and second F comes from PMOS. And we have SS, so slow, TT, typical. And we have FS, that is fast and slow. And we have SF, that is slow and fast. So all these abbreviation points to the speed of the NMOS and PMOS of a balanced CMOS. We're done with this particular slide, so let's move on. FEOL corners, detailed nomenclature. In last slide, we have shown you the most common nomenclature that is used. However, there can be more detailed nomenclature somewhere you may find in the VLSI industry. Here, let us get us familiar in advance. NMOS can be slow, typical, fast, corresponding to S, T and F. PMOS can be slow, typical, fast, that is S, T, F. Temperature can be hot, typical and cold, corresponding to S, T and F respectively. VDD can be high, typical, low, corresponding to F, E and S respectively. Elaborate process corner labels may include NMOS, PMOS, temperature, VDD. All of them may be included in the name. TTTT means typical NMOS, typical PMOS, room temperature, nominal supply. SSSS means slow NMOS, slow PMOS, hot temperature, low supply. FSSS means fast NMOS, low PMOS, hot temperature, low supply. So with the mapping provided in the first 4 bullets, you can construct many as such elaborate process corner labels. So we are done with this particular slide. Let's move on. Process corner variation. Here we will give a typical prototype of variation in this particular slide. There will be no exact values given here for the figure of merit. However, the structure of this table remains same for different figure of merits. Without any further delay, let us go through. Here are the columns, and first in this case VDD is fixed, that is the voltage, that is V is fixed. Here temperature is -40, then 0, then 27, then 80, then 125. And here we are varying the process, that is FF, and all the figure of merits will be listed in the table. As I have mentioned, we are not mentioning any value. Here the purpose of this slide is to make you familiar what kind of table you will expect in different kind of data sheets. TT, here goes the figure of merits, and here goes the SS. Then goes the figure of merits. So here I have just shown you the FF, TT and SS. In actual datasheet, you may have elaborate or maybe variation or maybe some of them or one of them. It depends upon what datasheet you are getting. This is a typical table what you can expect in datasheet of maybe a IP or something which you are getting from a vendor, and the datasheet is coming to you with all the process variation details. There you will expect such table. Now again we will do some variation here. Here we are keeping the process fixed. -40, temperature we are varying in the first row. This is same as the previous slide, and here in the first column we will vary the voltage, that is V. 1.63, and for that we will expect different figure of merits for a particular thing. Next we have another VDD, and here goes the figure of merits. we have another VDD variation, and we will expect the figure of merits. So these are the two tables you can expect in a data sheet. The previous example, that is the previous slide and this slide, in which one there the voltage was fixed, the process was varied, and the temperature was varied, and here the process is fixed and the voltage and the temperature is varied. So for the PVT, one is kept fixed and other two are varied in a particular table, 2D table like this. Now you are quite ready to interpret the different figure of merits coming into the data sheet from your vendor, from you are getting maybe IP or something else. We're done with this particular slide, so let's move on to the next slide. Real corners, FEOL and BEOL combined. So here I have kept this slide specifically for you because when you go into the actual IP distribution, what you get as a standard cell, maybe you will go there and see there are combines corner where the FEOL and BEOL are combined corners. So names will be like that, and that time you may become confused. So in advance I am clearing your confusion here. So here our nomenclature, this is a process corner, FF 1.2 volt, that is VDD, 125C. And next one is SS, the VDD is 1.05 and minus 40 is temperature. Next we have the typical, and we have the VDD is 1.05 and the temperature is minus 40. Now for each of these process corner, you may have BEOL corner. So these are the FEOL corners name, the process corner name also have the alias FEOL. Now the BEOL or the RC corners under each can be P based C volts, RC based RC volts. Similarly, others will have the same thing. Now, you can expect this kind of variation or permutation and combination in actual data sheets. So don't get scared once you have this. So you are now quite ready to face the data sheets where all these things are written. We're done with this particular slide. So let's move on. Summary. Process corners are visualized through imaginary 2D parallelogram. I have shown in the graphics slide. Each corner resides at each of the vertices. Only the typical corner reside at the junction points of the diagonals. Process corners are also referred to as the FEOL corners as per the semiconductor fabrication process. And this was the reason why I have shown you the CMOS layout, because the process corner will impact the FEOL, which is creating the layout of the basic semiconductor structures. Not only process but also voltage and temperature are included in the real applied corners. Variation of specific figure of merit of any design under consideration are observed across the permutation and combination of P, V and T. This permutation and combination can get complex with BEOL, that is RC corners, when they are taken into consideration. So that's all the summary, and we are done with this slide. So let's move on. Hey guys, welcome back. In today's episode, we are going to discuss the below points. RC extraction in ASIC design flow, post layout parasitics visualization, net resistance and capacitance, an overview so that those who are beginners can understand the significance in a deep manner. RC corner and their alias in VLSI. Technology node versus the RC corner relation. Corner terminologies, different corner terminologies in VLSI. Real corners, the PVT and RC corner permutation and combination. We'll discuss the impact of RC corners, that is the improved timing sign-off. And finally, at the end, we will summarize our entire discussion. So that's the menu for today. Without any further delay, let's begin. RC extraction in ASIC design flow. The ASIC design flow is also known as the digital design flow, where we design a system on chip, that is SoC, and in this particular slide, we'll focus at which stage the RC extraction happens so that you have a bird's eye view. First, we have the design specification and our flow will go in this direction where the arrow is pointing. Next, we do the RTL coding based on the design specification that we received in the previous stage. Next, once the RTL coding is done, we do the verification of the functionality of the RTL code. Next, we do the synthesis for the finalized RTL code. Next, we do the power routing. Then we do the global placement. One thing to mention here, that after synthesis, we are entering into the backend, and before the power routing, all the stages are in the front end. Next, we have the detailed placement. After that, we do the clock tree synthesis. Next, we do the global and detailed routing. Our flow now will proceed in the arrow direction as shown in the right hand side. Next, we do the layout generation or changes, whatever is applicable, because many times one particular stage in this entire flow is repeated multiple times until the perfection is reached at that particular stage. After this, we do the DRC and LVS, that is the design rule check and the LVS. Next step, we are doing the parasitic extraction. After that, we perform the static timing analysis. Just to mention here, this is the post layout static timing analysis. There is a similar static timing analysis happening at the front end that do not include the parasitics. And in this particular stage, the post layout static timing analysis, we include the parasitics from the spec file. Next, we do the EM and IR analysis. After that, we do the LEC and the final tape out checks. And once everything is finalized and whatever iteration needed at which step as required are done, and we are reached at some stage where we have no further modification or correction to be made, we go for the tape out. So this is the entire flow in the ASIC design. So here you can see the parasitic extraction I have highlighted in a different color. And at this stage, the RC extraction, that is the RC corners, come into picture. We extract multiple netlists based on various RC corners at this particular stage. This is the overview of the position of the RC extraction in the entire digital design. So with that note, let us move on to the next slide. Post layout parasitic visualization. As the name suggests, here we will just visualize what happens in the pre-layout and what happens in the post layout. So in the pre-layout, this is our netlist and all the gates and the resistors and capacitors here are part of the design. That means they are not parasitics. Those are part of the design. And what happens in the post layout is that what we get from the space, we back annotate goes into the actual design to have the effect of the parasitic R and C's as highlighted in two green circles. Here I have only shown the resistors. However, there will be capacitor. All these things will be there. Now, once we do this post layout static timing analysis with all the resistor and capacitance from space annotated into the simulation, we get a much more realistic delay, and that helps us to fine tune our design. That is the realistic part of the design. So I think discussed here in a short and sweet manner what the post layout parasitics are there to use for. So with that note, let's move on to the next slide. Net resistance and capacity. So here in this slide, I'll briefly show you the basics of the resistance and capacitance, that is the parasitic resistance and capacitance associated with the nets. I'll take the help of some infographics here and text combined. So here you can see that multiple nets are there, and the thing common is that they have similar structure but various lengths. Each 2-pin net that uses inverter cell for both load and driver. So here the red line in between the two inverters is the net. And here I display the basic capacitance structure, that is the two plates, and in between there is a dielectric, the area, the thickness of the dielectric and the area of the capacitive plates. Why it is important, I'll come to that point. R and C values are varied by varying the net length. So this is the length, this is the net length. Now, the capacitance come from the overlap of the two nets, and these two nets are two different metal layers, and in between they will have the separating dielectric, and this combination, as you can see in the right hand picture, will act as a capacitance, and this is a parasitic capacitance. This is not a design capacitance because it is in the BEOL layer, that means above the silicon. Also, the overlap increases as the net length increases. So, according to that, the capacitance will also vary. The resistance is proportional to the length of the net. That's a very straightforward relationship, and the capacitance will also vary with the overlap, because when two nets are running parallel, right, to each other, the area they are overlapped with, that area will act as a capacitor as shown in the right hand side picture. The R value increases with the increase in length. The C value increases with the increase of the overlapping length of the two nets. In actual chip, similar thing happens inside the BEOL metal or via routing. So that's in a nutshell. You can visualize where these R and C of the RC corner are coming from. So in this slide with the text and the infographics, I have explained to you about the basic net resistance and the capacitance. And with that note, let us move on to the next slide. RC corners in VLSI. So here I have displayed one graph. Here in the x-axis you can find the resistance here, and in y-axis you can find the capacitance. And there are vertical lines here in the resistance axis and horizontal lines here. Obviously these are again vertical to the capacitance. So here the capacitance value is fixed, here the capacitance value is fixed, here the resistance value is fixed, and here the resistance value is fixed. Now these lines are Cmax, the blue line. The green line is Cmin, the red line is the Rmax, and the pink line is the Rmin. Now, from where all these things are coming? So these will be there from the PDK. I'll come in which file format you will get. I'll come to that point. And these are the boundary limits of the maximum and minimum for both the capacitance and resistance. Now, I'm again emphasizing these are parasitic resistance and parasitic capacitance, not the design resistance or design capacitance. Those are used for the functioning of the design. These are extra. And these are coming from the fabrication process. Now, this is a corner. I've just highlighted with a light yellow circle what this particular corner is called. It is the forced cap. So here you can see the capacitance is maximum. So it is called the forced cap. Here, there is another corner. It is called the RC forced because here product RC is forced because of the R is maximum here. Here, this particular corner is called the RC best because here R is minimum. And here, this particular corner is called the best cap. That means the capacitor value here is the minimum. So, a question comes to your mind, right? From where all these boundary corners are coming into the picture, how I will define them? These will come from your technology file. While extraction, you have to specify a corner file. There, you have to pick up a particular NXT-GRD file from your PDK, which will correspond to each of the available RC corner. That means your foundry supplies you the NXT-GRD files for the extraction, and these corners are predefined to you. These RC corners are very much predefined from the foundry. You just have to remember this graph, understand the significance of what each corner is called and how they are going to impact. I'll come those impact factors later on, but this is a very important graph. You just understand and visualize this thing, keep it in your mind. So we are done with this particular slide, so let's move on. RC corner name alias. Now here I have used couple of corner names in the previous slide inside the graph. However, from company to company and foundry to foundry, several names can be used for the same corner. So by physics, these corners are same. However, the names can be a little bit different. For your knowledge, I am sharing all the names that could be tagged along for a particular physical corner. Here I am drawing the lines. Okay, this is not a tic-tac-toe. We are just keeping the names here. So here first Cmin, it can have another alias Cbest and also best cap. So these are aliases. So you pin into your mind. Next comes the Cmax, which is also called the C-worst. Also, it is called the worst cap. So in the previous graph, you can get from your foundry with any of the name attached among these aliases I have just mentioned. So let me draw a horizontal line, and next comes the RC min. RC min is also called the RC best. Also, it is called the best RC corner. So any of the names can appear to you. Next, we draw a line and we come here as the RC max. Now this RC max can also be called as the RC worst. Also, it is called the worst RC. So in the horizontal line, or rather in the rows, the names are aliases. Okay. And any of the terminologies you can come across. Generally, a particular naming convention is followed in a particular foundry and you will find them. So you can keep this particular table with you so that you do not get confused when you start working and you get the PDK and you get the corner names. So with that note, let us move on to the next slide. Technology node versus RC corners. At higher process node greater than 90 nanometer, overall delay is governed by the cell alone and delay due to the interconnect is ignored. Therefore, total load depending on the number of fan out is represented by the capacitance only. So this is the picture above 90 nanometer, say 130 nanometer or 180 nanometer. All those nodes will have this kind of characteristics as highlighted by these two bullets. Consequently, foundry provide two parasitic corners, that is Cmax and Cmin, which correspond to maximum and minimum delay respectively. Now, what happens below 90 nanometer when we scale down? The settings RC based and RC worst result in the lowest and highest interconnect RC products respectively, whereas the best cap and worst cap result in the lowest and highest interconnect capacitance values. Therefore, for paths with long interconnects, corners RC based and RC worst will give the smallest and largest path delays respectively. It's very easy to understand. You can see from the product of R and C. Paths with short nets, it is corners, best cap and worst cap that cause the extreme path delays. We are done with this particular slide. Let's move on. Corner terminologies in VLSI. So here in this particular slide, we will talk about various type of corners, that is not only the RC corners, and we'll expand our view for the other corners and we'll have a bird's eye view. So that's why I have kept this slide. So let us dive in. There will be front end corners and there will be back end corners. Now, what are the front end corners? These corners you can find in the timing.lib file. There you can get the corner files. Back end corners you will find with the RC corners we have just discussed. So what are the front end corners? Fast, that is abbreviated as FF. Slow, that is abbreviated as SS. TT, that is typical, that is abbreviated as TT. Now, there will be combination of F and S, that is fast and slow, that is FS, or SF, that is slow and fast. So these are front-end corners. These are typically the process corners, and here we are not talking about the voltage and temperatures. Now, let us move on to the back-end corners, which are basically the RC corners. So they will be C worst, C best, CC worst, RC best, and RC worst. So here you can see a new terminology, that is CC. Yes, the coupling capacitance I think is very important, below around 20 or 25 nanometer. Any node available there, the coupling capacitance also come into the picture, and you will come across these particular coupling capacitor corners also from the foundry. Now here we have two different set of terminologies for front end corners and back end corners. At left we have the process corners and right we have the RC corners. So you have a glimpse of these two. Now let us move on to the next slide. Real corners. Now, after defining all these corners and their types in the previous slide, now let us see in actual practice when you have the design kit, which includes the PDK as well as the standard cells and all the other IPs. I have created one particular video on this. You can find it in the FAQ playlist. So here, once you have those set of design kit, all these things included, you will have combination of PVT and RC corners. So there will be combination. And how does this combination happens? What ratio? These are mixed. Just to have a visualize, I'll take the help of the infographics here and let's start. So this is the process. Here is fast FF, voltage is 1.2 volt and temperature is 125 C. This defines one particular PVT corner. The next PVT corner is SS, the voltage is 1.05 volt and the temperature is minus 40. Okay. Next, we come to the third PVT corner, that is typical, and then we have 1.05 volt as a voltage, and then we have the minus 40, that is M40C. So these are three examples. There could be many combination and permutation in these corner names, as you can easily assume from the previous slide, all the process corners, or there will be variation of voltage or temperature. So there could be multiple combination of these. So let us just for example take these three, and inside them what we will have. Here there will be C based, C worst, RC based and RC worst. So one particular PVT corner will contain 4 RC corners. The same will happen again for the next PVT corner. the same is going to happen for the next PVT corner, and so on. So in this way, the PVT corner and the RC corners are combined. That means for one particular PVT corner, there will be 4 RC corners, or if there comes a coupling capacitor corner, one or more than one, then they will also be included. So this way, the realistic corners are available in the design kit. So you will find in this way, the nomenclature, the naming, the file name or the folder name, you have to understand by comprehending the meaning and the terminologies that I have supplied here. So with that note, let us move on to the next slide. Here in this particular slide, we are going to talk about corners, all the kind of typical permutation and combination. Some of the things I have already shown you, and some more information I will give you here as text. Generally, there are 3 process corners: best case, typical case, and worst case. The best case contain fast process, high voltage, and low temperature. These are very straightforward, so I am not going in the explanation. The worst case contain low process, low voltage, and high temperature. The typical case gives the nominal performance. Also, generally 5 RC interconnect corners will be there: mean C, mean RC, typical, max RC, and max C. Thus, the total number of combination is process corners multiplied by RC corners, that is 5 into 3, 15. Now here, if we include the variation of voltage and temperatures, the total number of combination of the corners will increase further. So as I mentioned, if we include the voltage and temperature variation, then the number of permutation and combination will increase further. That's all with this particular slide. So let's move on. Here in this slide, we will talk about the impact of the RC corners. Where does it impact and how significant this impact is? We'll take a help of an infographics. In this arrow direction, the flow will go on for the infographics. First, we combine the netlist and SPEF parasitics for the post layout simulation. I have already had explained in the, I think, first 2 slides about the annotation of the parasitics from the SPEF into the netlist. Next, as mentioned, all the RNCs will be back annotated inside a tool. And here we perform the STA with the high accuracy. This is a post layout STA. And then we sign off with a high accuracy. So overall, we have the parasitics, we annotate them, we do the STA, and finally, once we clear out all the violations and optimize our STA for the timing requirements, we have a high accuracy sign off. So this is the point where the RC corners have its final impact. So that's all with this particular slide. Let's move on to the next slide. Summary. Here we are summarizing all the points we have discussed so far. For technology node down to 0.35 micrometer, the delay estimation is based on well load model, which can be accurate few iteration for timing closure. For technology node 0.25 micrometer and below, we find RCCC distributed effects become very much dominant for delay model. We also find many voltage domains coupled with operating modes. We easily get numerous corners with setup and hold analysis for each and every node. Hence, the RC extraction we have to consider for worst case, nominal, or the best case. In the entire discussion, we have excluded the temperature inversion corners, which is a different set of entities. We are done with the summary. Let's move on to the next slide.
Hey folks, welcome back to the computer screen. In today's episode, we are discussing viewer Rajeshree's question, what is the difference between AOCV and POCV, which she has asked in the 18th episode of Q&A, where I have discussed about POCV. Now, in all the previous episodes in the static timing analysis series, OCV and POCV is discussed. So today we are going to discuss about the AOCV. So let's move on to the next slide. In today's episode, we will be discussing about what is AOCV, which is also known by another name LOCV, working principle of LOCV or AOCV, understanding the LOCV or AOCV derating table, timing dotted data format or AOCV or LOCV, the analysis types of LOCV or AOCV. So that's the menu for today. Without any further delay, let's begin. What is AOCV or LOCV? So This AOCV is implemented for intra-die, that is single wafer timing variability analysis. This point is very much same as the OCV. However, it is less pessimistic than the traditional OCV, which has a fixed derating value. Means that the derating is a kind of constant everywhere for every gate, and it do not have any kind of distance or path relationship. It's just a static number. So in actual practice, when there is a wafer and the process through which the semiconductor chip is made, all those variations, the process variations happens various parts of a single wafer itself. If you traverse from one end to the another end of a single wafer, there may be difference. The difference can be found even for a single process step. So how can the effect be same or very pessimistic? However, these AOCV things became very prominent around the 65 nanometer node or below. Above 90 nanometer node, there was no need to see about AOCV or LOCV. But in the sub-nanometer domain, when we went down around or below the 65 nanometer node, that time this AOCV has a great importance. Derating is a function of path or graph in AOCV or LOCV. So as I just mentioned, that if I go from one end to the another end of a single wafer, how we move on top of the wafer, definitely there will be a path. And the graph is another concept in VLSI, especially in timing. So derating here in AOCV is a function that is dependent on path or graph. Hence, the name is appropriate, location-based OCV. Why it is important? Because this location-based OCV, the locations are determined by the path. Hence, the name is much appropriate, the location-based OCV. Or the more popular name of it attached to it is advanced OCV, that is AOCV. In the industry, the less common name is LOCV and the more common name is AOCV. So we are going to mostly call by the name advanced OCV or AOCV. This is a non-statistical method as compared to the parametric OCV, that is POCV. The POCV already we have discussed in the last episode of Q&A, and that was a statistical method. However, this is not a statistical method. It is an advanced version of the Ponzi variation, where we take the consideration of the derating variation depending upon the path in traversing one end of the wafer to the another end of the wafer or the single bit. However, in these paths, there will be logic gates. We are not moving randomly. We are done with this particular slide, so let's move on. Working principle of LOCV or AOCV. In this method, the cell or gate derate varies with logic depth, that is hierarchy, and based on the path or graph. Logic depth, you understand that the gates are connected or the blocks are connected and we go inside a block, we have a sub block. This way we have the logic depth or the hierarchy. This path may extend from one end to the other end of the same chip, that is the wafer. Already I have couple of times mentioned this thing. Such path may not consist only a single type of gate, rather various gates. Obviously, the design will contain multiple types of gates inside the silicon wafer. In this path, equal and opposite kind of derating may partially or fully neutralize each other's effects. This is theoretical. In practical, you can see it may happen, it may not happen. There is all type of possibility. Derating values varies for each cell type, each depth, each location, each slew, and each load. You can understand the derating values are also dependent upon various factors as cell type, depth, location, slew, and load. Reading standard cell characterization to get the minute or accurate data, AOCV or AOCV requires a lot of library characterization manpower and hardware or software computational resources as compared to its ancestor, it is OCV. Now this is a very much important point, because to perform the static timing analysis, we have a very much needed input, the timing.lib, which comes through the standard cell characterization. Now, for this LOCV or AOCV, we require a huge amount of manpower and hardware or software resources. Manpower in the term that more man days rather than more people, it counts more man days, that is work weeks, are spent here on standard cell characterization. So this is one fact about the AOCV in the background, not in the HTA tool, but in the background requirement I, that is timing.lib. Worst case derating is picked up across each load or slew pair combination. So this is the part of the method. We have load slew pair, you know, from the timing.lib, right? So there we have the load slew pair and we have a LUT, and from there we pick the data. In case you have not watched the timing.lib episode in the STA series, go ahead. You can find it in the STA playlist and from there you can watch it. So folks, let's move on to the next slide. Understanding LOCV or AOCV derating table. As I mentioned that the AOCV or LOCV is a path or graph dependent entity. So the derating is not fixed here. It varies. How it varies? That is we are going to determine or see here. Here is a kind of representation of the silicon wafer. It's a hand drawing. So here the oval represents a silicon wafer and on the arrow is a path where we have the logic gates in the path, and the numbers there you can see 0, 1, 2, 3, etc. give the logic depth. And how we have the derating table, this picture will help you to understand. Here goes our derating table. First, we have indexes as depth, that is 0, 1, 2, 3. Then we have indexes as 200, 300. The units can be found at the top of the .liberty file. I have mentioned in the timing.lib file. We have already explained what is there in the header section. These basic units can be found in the header section. Next comes the table. So you can see there are 1, 2, 3, 4. 4 columns and 2 rows. So these 1, 2, 3, 4. So this goes for the columns and these two goes for the rows, and thus we create a PD table to get the corresponding derating. So thus the derating can vary. This is the AOCV table. I have just give you a kind of snapshot from the actual table. I will show you the actual table later on, just for your understanding, just to create the right impression to your mind. This slide is created. Just take a snapshot in the mind. Yes, in upcoming slides we are going to discuss about the actual table. This is the actual data, but the table consists of much more data, but this is the crux of the table where we have the variation of the derating. We're done with this particular slide. Let's move on. Timing.lib data for AOCV or LOCV. So here we are going to come across the actual table. So first there will be a header section of the table where these things are mentioned. The library, OCV lib, then OCV table template, would be OCV template. This is the name. Then variable 1 is path depth. Variable 2 is path distance. Now you can see that we have named it. This is a table prototype. It is declared in the top section of the .lib. And we have dummy indexes 1 and 2. In actual case, these indexes, values and numbers can vary. And here we close it. So this is the template, that is the prototype of the actual table that we find later on inside each cell of the .lib file. Now what we see in the actual cell inside is every cell definition. Let's look into that. Here in the bigger rectangular box we will be displaying that. The first we have default OCV derate group, that is advanced OCV. Next we have the cell name. Then we have OCV arc depth 2.0. So this OCV arc depth is the effective logic depth of a cell or a timing arc. We have a value here. OCV derate group, AOCV 1. Then we have OCV derate. Here it begins. OCV derate factors is 2D OCV template. And RF type, it is rise fall type. And here in this particular cell, it is rise and fall. However, the valid inputs can be seen in the right hand side as comments, right? The valid are rise, fall and rise and fall. So these are the types. Next, the derate type is early. This is the type of the arrival time. So it could be early, it could be late. These two values can come to here. Next, the path type. So here the path type is clock and data. And the valid types are clock, data and clock and data. Now here comes the actual indexes. Next, we have the second index. So here you can see from the prototype, the index number and the values have been changed. Next, we have the values. That is the table, actual 2D table, lookup table. So here the table closes. So already you can now correlate. In the previous slide we have discussed these two things and this thing. We have visualized in actual the timing lib. So this is written in this way. First this template is defined somewhere up in the dot lib, and later for each cell this section comes for the AOCV, and the relevant strings I have kept here. So this is a short and sweet description of the data that can be found in the timing.lib that has to be characterized by the standard cell characterization in, and this particular data requires a lot of effort. There could be various variation even for a same cell. So every possible combination has to be logged there inside the .lib. So I have just given you one snapshot. And if you see right here the values rise, fall, rise and fall. I am moving my mouse, so clock data and clock and data. So all these combinations, multiple combination of these variables can be there. Next, analysis types of LOCV or AOCV. There are two basic types of the LOCV or AOCV. In this slide, we will also see the snippet of the commands that are going to use. So first, see, to enable the AOCV, we use this particular command in the ST tool, timing AOCVM enable analysis, and the value is true. And this invokes the AOCV ng to read the respective AOCV inputs and process the design accordingly. Now, the first type is graph based. As we mentioned, to initiate this particular method, we use report AOCV and this particular command. The first command already invoked that enables AOCV, and the second one invokes the graph based method. The second method is path based method, which is invoked by the report timing and then dash PDA mode path. This way you can invoke the AOCV method inside the ST tool. Obviously there will be a lot of other commands, but these are the key commands that you have to put here. So folks, in a short and sweet manner, we have covered this particular slide. Let's move on. Hey guys, welcome to the 6th episode of static timing analysis. We have so far talked about the various theoretical concepts. We will be focusing on the STA input files for next couple of episodes, starting from this episode. Today, we focus on the very important input file called timing library file. Also, sometimes you call it the .lib file. You can see in the rightmost corner, the timing library, that is the Liberty file, is highlighted in green circle. These files have a .lib extension, and these are human readable ASCII file, that is text file in simple language. We are done here, so let's move on. As you already know that we are exploring the timing library file here in this episode. So today's learning breakdown for the episode is how Liberty file is created, Liberty file introduction, Liberty file internal format and sections, internal format, name tokens and their meaning, header, LUT, cell, all this section definition, lookup table, LUT section, various standard cell sections inside the Liberty file with example. We are done with this particular slide, so let's move on. How Liberty file is created. In this slide, we will discuss the Liberty timing library creation in a nutshell. Here are the representation of standard cells logic family. At synthesis level, you first need the gate level netlist for each unit logic gate. These are digital logic gates. We also have the sequential element such as flip-flop in the standard cell library. Inside the standard cell library, on single cell, we have various views like Verilog, .lib, that is Liberty, layout, DSPF, spice, CDL, schematic, EMIR views, etc. In the standard cell characterization, the engine picks up the necessary views for the characterization and runs the dynamic timing analysis, which is already explained in episode 1. In case you have not seen the episode 1, request you to use the chapter facility in the respective video description to quickly navigate and see the relevant section. Now, the characterization process gives birth to the FE, that is the text output file called the .lib file. Now, let us get a bit closely familiar with this file. Let me give you the brief introduction to the .lib file used in the static timing analysis. Timing engine reads a set of tails library files, that is .lib file. So this is mean to say that the timing engine could read more than one .lib file depending on your design in actual VLSI chip making area. The .lib file is a text file containing timing and power parameters associated with any standard cell for a given technology node. Now here one term I would like to explain, that is the technology node. You might have heard it's a 2 nanometer chip, or it's a 5 nanometer chip, or it's a 10 nanometer chip. So this nanometer number that you are getting nowadays on the chip is the technology node. However, each company has their own method to describe this technology node. You can take the ITRS technology roadmap for a standard where they define that the technology node, that is the nanometer that we speak for any of the chip, is the DRAM half pitch. So the distance between the DRAM half pitch is called technology node as per the ITRS guidelines. Now the .lib file contains not only timing but it also contains the power parameters. That is one more thing you getting to know here. And this .lib for a technology node will contain the exhaustive list for the timing and power parameters for all the logic gates, sequential cells, etc. And there will be a couple of special cells also. Those special cells I have explained in the UPF video. You can go there and see. Also, I'll put the link in the description. It contains the data for all standard cells available in the design in the specified technology node. I have just mentioned it. So each instance in the Verilog VHDL or system Verilog netlist must have a corresponding cell found in the .lib library. So guys, whenever you are reading the files inside your timing engine, there you load your Verilog file, then you load your .lib file. So that loading of these files will go to the temporary live database, that is the design database that is with the timing shell, that will automatically map the corresponding Verilog and its corresponding cell sections from the .lib file. It will do with its intelligence. The .lib file contains pre-characterized timing models and data to calculate IO path delay, timing check values and interconnect delays. So whatever data we have in the .lib file, they can calculate all these things. To compensate the PVT and OCV variation, derating factors are also included. I have already explained in some of the previous episodes about this PVT and OCV variation separately in detail. So all those derating factors means when this variation happens, we include derating factor so that we can actualize the PVT and OCV variation inside the static timing analysis. We are done with this particular slide, so let's move on. Liberty internal format. Let's look into the internal structure of the Liberty file. If you directly open the .lib file with any text editor such as gbim or gedit, etc., what you will see, the vastness of the data mining inside the file. The data mining is done in a very efficient structural format. We can broadly classify the content inside a .liberty file in 3 broad sections and their subsections. So the sections are like this. There will be a header section, the LUT, that is lookup table section, and third, the cell definition. So these are major sections inside the .lib file. And in this presentation, I will go to the definition plus example of all of these sections in upcoming slides. So we are done with this particular slide. So let's move on. Name tokens and their meaning. Before jumping into each section and analyze them in detail, let us get familiar with few frequently used name tokens and their meaning. These have very straightforward meaning. Some of them I have already explained theoretically in some of the previous episodes. So here we go. norm temperature and norm voltage. These two name token specifies the temperature and voltage reference points, that is operating condition. Slew and delay threshold points. Low and high threshold values for slew calculation 10% to 90% and the threshold for delay calculation, that is 50%. I have pictorially made these things clear in previous episodes. These name tokens will be there in the .lib file to specify these 1090 or 8020 threshold and the delay threshold will be 50%. Default values for fan-out capacitance slew specifies the limits of maximum input slew on an input pin, input in-out pin capacitance and the maximum output capacitance on any output pin units. So these name tokens also be there and from there you can interpret the values. So we are done with this slide. So let's move on. In this slide we continue further for some more frequently used name tokens and their meaning. Operating conditions, derating factors, limits, and units. Three different values are usually required, that is typical, worst, and best case. These tokens will be also there, but their values will be typically key values, typical, worst, and best. However, to accurately get these three values, process, parameters, and transistor models for the entire process are required, which is only available through foundry provided PDK or tech files and used during the pre-characterization stage. So a couple of slides back, I have mentioned that you get the PDK and the tech files from where the relevant files are picked up automatically during the characterization stage. Here we are re-emphasizing on this point. Library and delay model. Provide a library name and delay model through the table lookup, that is non-linear delay model. So some of the LUT I have already explained in couple of previous episodes, but since I am explaining the .lib or the timing library in general in this slide, so here I re-specify or we emphasize these details. Norm process property. Specify the reference points for process scaling used for the characterization of the cells. So these will give the scaling factors of the process. So these are very straightforward, so I am not going in detail and you will come across in the example all of these name tokens. Why we call them name tokens? The reason is that these will be fixed in the .lib file and these text will be fixed across multiple .lib files and they will have a value which may vary from one .lib file to another .lib file, but these name tokens will be fixed text phrases. I have already explained all of the common type of name tokens in the last two slides, so we are done here. Let's move on. Header section definition. The header section of the timing library file is important for both the ACA tool as well as the engineer who is doing the STA. Now, let us see the header section in generalized prototype. We start with the library name. In the angle bracket, the library name will be there. Then starts the header section. Here you can see the slash start and the start slash acts like a comment in the .lib file. There will be delay model. The delay model is table lookup, that is LUT. Time unit, it will be given the time unit in second or nanosecond or something like that. Voltage unit, it will contain the voltage unit. There will be current unit. There will be capacitive load unit. Sometimes we called the load, which also means the capacitance. That will have its unit here. It has two parts. One is the float and another one is the unit. Leakage power unit, pulling resistive unit will also contain the resistance unit. Then there will be norm process. There will be some double here. It is, you can say, the double real int, that double here we are mentioning. Norm temperature double, norm voltage double. Operating condition, in the angle bracket there will be actual instance name. Process double, temperature double, voltage will be double. We close the operating conditions here and default operating conditions, there will be an instance name. So this is the kind of detail of a header section that will what the details it will contain. Sometimes in the library file there could be some additional name tokens. In that case you have to interpret by the name and the meaning. I'm done with this particular slide, so let's move on. LUT definition. LUT is lookup table. The body of the Liberty Timing Library contains lookup table and cell definition. The lookup table or the LUT has a prototype defined in the topmost sections in the Liberty file and just after the header section. So here we define the prototype and later on we use it. You must remember the variable values are subject to change in the data populated LUT inside timing block of each cell definition section. So here we are starting the LUT prototype definition. Lookup table template definition. This is a comment. LU table template and there will be the table label or the name. Variable 1, then variable name. This will be a text. Index 1, ping of the data points for variable 1. So if this variable I have 5 different values, then there will be 5 values mentioned inside this index 1 values section. Variable 2, the variable name, and similarly it will have the index 2 and set of data points for variable 2. And here we close the LU table template. And further such more template definition will follow. Such multiple LUTs are defined for each particular data set at the beginning of the library file. Thus, for example, I can say that you are having multiple LU template. One thing could be for delay, one thing could be for rise, one thing could be for fall. We will come and see the examples later on this today's episode. We are done with this particular slide, so let's move on. Standard cell definition. For each standard cell, we have a standard data structure for its data mining purpose. In this slide, you will get familiar with this general structure. Here goes our comment, cell definition, then cell, then cell type, pin name, direction. So here just I'd like to emphasize cell type means whether it will contain the name. From that you can check whether it's a logic family or it's a sequential or it's a latch, etc. or it's a special cell. Now we continue again. Clock, that will be Boolean. Max capacitance will be there, that will be a double value. Mean capacitance, that will also again have double value. So these are the upper and lower cap. Then starts the timing block. Related pin, then it will be pin name. So this is very much important. Now if you look here, we already started with a pin. Pin means the cell pin on which we are having all this data, and timing is always between two pins. Whatever AT RAT we define, that is between the two pins, and here the pin and the related pin are the 2 points in between which we are having the timing data. So these two are very important. Combinational or sequential definitions will come in the next section depending upon the cell is a combinational type or a sequential type. Then we close the timing. There could be more timing definitions. As per the number of pins, the more pin sections will follow. Here goes our more pin definitions that I was talking about, and the more timing definition will contain the details of the timing. Now here we close curly bracket, we have closed the cell, and the next we have more cell definitions. Now again we totally close here. So this is the kind of cell type definition, and this is a typical structure you will have inside the LUT. Whatever the cell type is, whether it's a logic family or it is a sequential or it's a latch or it's a special cell, here will be cell section. This is mask. One more thing not shown here is the functionality. This is a section that contains the truth table representation for combinational cells and present state versus next state table for the sequential cell. This is well understood by any human eyes. We're done with this particular slide, so let's move on. Flip-flop and latch definition. Now let us have a quick look into the flip-flops and latch structures. The same structure is applicable for all general flip-flops. Flip-flop, state of non-inverting output and state of inverting output. Clocked on, then there will be a clock pin name. Next state, input combination that produces the next state. This is typically looks like a equation. Clear, active value of the clear input. Preset, active value of the preset input. Clear preset variable 1, value of non-inverting output when both are active. Here preset variable to value of the inverting output when both active. Here we close the flip-flop. Latch is very similar structure but requires enable and data instead of the clock and the next state. So this is a kind of general structure for the flip-flop and latches. We are done with this particular slide. Let's move on. Scan change cell definition. Apart from the regular cells, special cells which are used in the DFT purpose are included in the library file or the timing library file. These are termed as scan change cells. We also have scan flip-flop in the timing library file. Let us see the scan change cell structure. Requires a test cell group to be defined. So this is about the structuring of the .lib file. Two flip-flop groups need to be defined, one in the cell function defined with testing features and one inside the test cell group without the testing feature. So there will be two sections where we have the presence. Test cell. Then come test scan in. Scan input pin name here goes. Test scan inverted. Inverted scan input. Test scan out, can output pin. Test scan output inverted, that is inverted scan output. Test scan enable, high on this pin puts in the test mode. Scan and shift. Test scan enable inverted, same as above but inverted. Test scan clock. The test scan clock for clock scan. And here we close the test cell. So there will be two instances, one inside the test cell group, another in the regular section. So thus the scan chains are defined. One thing to mention here that the scan flip-flop have the similar structure as regular flip-flop mentioned in the last slide, and these are used in the testing purpose of the chip. So we are done with this particular slide. So let's move on. Let's see some example. We came across all the definition blocks so far. Now let us plunge into the examples to fortify our knowledge gained so far with example. Header section. In this and next slide, we will exemplify the header section. So here we start the library simple. Here you are getting the example. So actual names and values will be there. Delay model, table lookup, time unit 1 PS, voltage unit 1 V, that is 1 volt, current unit 1 milliampere, leakage power unit 1 microwatt, capacitive load unit. It has two parts if you remember. First one is 1 and second one is FF. Cooling resistance unit 1 kilo ohm, default fan out load 1.0, default in-out pin capacitance 0.0, default input pin capacitance 0.0, default output pin capacitance 0.0. We continue again. Slew load threshold PCT rise 20.0, slew lower threshold PCT fall 20.0, slew upper threshold PCT rise 80.0, slew upper threshold PCT fall 80.0. So here in these 4 lines we have just explained the thresholds, that is 20, 80 in the slew. Input threshold PCT rise 50.0, input threshold PCT fall 50.0, output threshold PCT rise 50.0, output threshold PCT fall 50.0, norm voltage 0.7, norm temperature 70.0, norm process 1.0. So I would like to mention one thing. Here you can see that in the right hand section you can see rise fall rise fall rise fall for all of these thresholds. This is because in actual transitions the inclination of the rise or the slew transition may not be same. So explicitly we define here both of them. So we are done with this example of the header section here, and we have it continued in this slide. operating condition typical underscore 1.0, process 1.00, temperature 70.0, voltage 0.7, p-type balance tree. We close the operating conditions. So here you can see the operating conditions as process temperature voltage, that is PVT values. Default operating conditions typical 1.0, LU table template delay output slew template 7/8, variable 1 total output net capacitance, variable 2 is input net transition. Then comes the variation of the variable 1, that is index 1, means the total output net capacitance. These will be the values on which we have done the variation. Index 2 have a set of variation values here, and we close the LU table template. In upcoming sections, this particular LU table template will not be mentioned. Only the explicit table will be there. So there only index 1, index 2 or variable 1, variable 2 will be mentioned, but these names will not be there. I emphasize the names will not be there in the example in upcoming slides. And one another thing, in the above section, in the operating conditions, we have kept 1, there could be more than 1, and the default one will be picked up by the default operating conditions. We are done with this particular slide, so let's move on. Cell begin and end. Each cell contains huge amount of data that varies from one cell to another. So we will segregate each section and look into them separately. Here in this slide, we will look into the beginning and end block of any cell because this part will be common. So the begin section of the cell, here goes our example. Begin cell, this is a comment inverter X1. So it's an instance name X1 and the type is inverter. Cell inverter underscore X1. Then pin O, direction output, capacitance 0.0, max capacitance 12.80. Now here we define the capacitance values and the capacitance unit already we have defined in the header section. Mean capacitance is 0.0. Start timing. After these definitions, the timing section inside the cell will begin. Now we see the end part of the cell. Related pin A, this is very important that I have already mentioned because when you talk about one particular pin O, we just kept in the left hand section, the timing always require 2 pins from and to. So these are those 2 pins. One is the pin which we are having the definition part and the timing is related with respect to the pin A. Here we close the timing, end of the timing. We go here, end pin, the pin is closed. Next, the next pin comes, pin A, because the inverter, there will be 2 pins, one is O and another one is A. It has capacitance 1.0, direction input, and we close pin A. We end pin here. So these are comments, the star slash star and then the star slash defines the comment. We close it and then we close the entire cell, end cell inverter underscore X1. So thus the beginning and the end of each cell will be there. Inside the timing block there will be relevant timing data. Since we cannot show in one single slide everything here, so that's why I have made the split into 2. One is the begin and end section of a cell and the respective timing section I will describe in the subsequent slides. As you can see that we describe each pin separately of a cell. The token related pin at every LUT section will connect the timing path between the 2 pins. We will see in upcoming slides. We are done with this particular slide, so let's move on. Before beginning, I would like to mention that here index 1 and index 2 we have described already in the header section. Index 1 is the total output net capacitance and index 2 is the input net transition. These two are also called the output load and the input U respectively. And here we start our cell output rise delay, the LUT lookup table. Cell rise delay output slew template 7 by 8. 7 by 8 gives the number of the row versus column of the table. Here goes our actual index values for index 1. I have mentioned already the index 1 and the index 2 just few minutes back. Index 2 has these all variations, and here goes our table. First row, second row, and we keep on adding the rows and the columns. Here our table gets closed and you can see. So let me bring my mouse. Here goes our row values and here goes our column values. That means index 1 and index 2. Here we close the entire cell rise, the delay output slew template. LUT section we have closed. Cell output rise delay of pin O with respect to pin A. Here related pin is A. This is a kind of I have emphasized here. I have already told, but I have emphasized here just to knock into your mind that the timing is always in between two pins, and we just started to describe the O. We left the timing section blank there. We have just kept beginning of a cell and end of a cell, and here now we are defining the timings inside each cell. Cell output fall delay, LUT. Start the timing. Cell fall delay output slew template 7 by 8. We have index 1 variation, index 2 variation, and here starts our table. Here starts our row, and we keep on adding the rows and corresponding columns, and here we close the table. Now why I am showing all these explicit examples? Because in our actual .lib file, that is Liberty timing file, all these kind of various lookup tables will be present. So I'm kind of knocking into your mind and with the example, so that you remember when you open and read a .lib file and you don't feel lost in the data. Yes, this all type of LUTs will be there. We close it here, and again re-emphasizing the point that this is the cell output fall delay for pin with respect to pin A, which we denote with the related pin name token, and the value is A. So we are done with this example. So let's move on. Cell output rise slew, LUT. Rise transition, delay output Q 7 by 8. Here goes our index 1 variations. Here goes our index 2 variations. Values, start our row, and we keep on adding the rows and corresponding columns. And here we close the table. And here we close the rise transition block. So this is the LUT for rise transition, that is rise slew. Cell output rise time of pin O. We are done. I have not talked much because I have already talked and explained in previous examples. So you can understand by your own about these names. And I have also mentioned earlier that rise and fall will be there because the slanting of the rise and fall transitions are not same in actual transitions, and hence explicit data for rise and fall will be there. We're done with this slide. Let's move on. Cell output fall slew, LUT. Fall transition, delay output table template 7 by 8. Now here goes our index variation, index 2 variation. We start the table values, first row, and then we keep on adding the rows, and the corresponding columns are automatically added. And here we close the table, and here we close the fall transition block. Again emphasizing cell output fall time of pin O. We are done with this slide, so let's move on. Thank you for watching up to this point. And don't forget to like, share and subscribe. If you have some Bizlaric, put it in the comment section below, and bye for today.